FTIR spectrometer that we will discuss in the next class. But before that, we will go through some important mechanisms or important process in FTIR spectrum that we will discuss now. Quickly, we can review that. FTIR spectrum. The basic principle behind this FTIR spectrum. So, when you consider this figure, okay, this figure is adding of sine waves and shows the superpositions. Shows the superposition. So, okay, I will discuss this figure. Okay. Okay, so the when you consider the normal IR spectrometer, for example, so we have to consider the prism rotation and the rotating grating. So in all those cases, we have to sweep all frequencies by rotating through all the frequencies by rotating that the prism or the grating. Okay, so getting each spectra, okay, I will explain by using that we can. So why we need this FTIR spectrometer, FTIR technique, or Fourier transform technique, spectrometer, is that we have to consider the grating pair or that prism technique. So the prism has to be rotated to get the different frequencies falling onto your mirror. So depending on the prism's resolution, we have the number of different frequency components that is coming out from that prism. And by using grating, we can have a large number of frequencies as compared to the prism, and the resolving power is high in that case. So we have an IR branch, or for example, near IR region, all those frequencies which are coming from the source and which is hitting on this particular. So from the source, all those range of frequencies are coming. Okay, then that hit in this prism, and that prism will make some dispersion effect, and individual frequencies are coming out from this prism at a different angle, and correspondingly we can rotate that prism in such a way that we get different frequency at different angle, and these frequencies are used by this IR radiation, IR spectrometer, and that is going. This is just a representation. This is not the actual IR spectrometer. Okay. So, and that will be going to your sample. For example, if this is your sample, and then from that it will be detected by using your. Okay. So this is a process, and the main drawback is happening here because we have to rotate the prism to get each and every frequency. And we have to plot it, like, for example, if you are having this kind of a spectrometer, and convert all those frequencies into centimeter inverse, that is into wave number, and use that wave number to plot this IR spectra. So let's say this is your frequency. For example, you are starting from some 400 centimeter inverse, which means that associated with that, we'll be having one frequency. Then in the next rotation, we have a next frequency. In the next rotation, we have next frequency, like that. It is coming, and we have some thousand, some, for example, some 600 frequency, 100 centimeter somewhere here. Okay. Okay. So with this frequency, we will measure what is the transmittance. What is the transmittance? So if, for example, when you consider that 400 centimeter inverse, which means that associated with that 400 centimeter inverse, we have one frequency which is coming from the source. That is dispersed by the prism, and which is coming from this mirror and going through the sample. And if there is no frequency which is frequency of vibration in the sample associated with that frequency, then that all the frequency will be coming out and detected by this detector. And measuring 400 and something else also is coming out. This one also coming out. And this frequency, there is some vibrational band associated with this frequency in this that particular that sample. This frequency also, there is some particular group which is absorbing that particular frequency, and we have something like this. And if you plot for all the frequencies, then we will get different bands at a different frequency position correspondingly like this. Okay. So this is what we do in normal IR spectrometer. So we'll get the spectra for the transmittance. We'll use that percentage of transmittance. So this is the process. So in this case, how many number of points you will get? It depends on your resolution of your prism and your the grating. Okay. And but we have to consider each and every frequency in this case. Even it is done by mechanically by the spectrometer, it will take some few minutes. For example, 15 minutes, 20 minutes, something. So in normal IR spectrometer, it will take some time to get the spectra from the for the sample. Okay, and if you want to have the same spectra to take again to avoid the noise, okay, to avoid the noise, to have a confirmation on the spectra, and you have to take these spectra several times, and you have to magnify this spectral intensity by using the same technique. Then it will take much more time. If you are taking the same spectra of the same sample many times in order to make sure of that, and to avoid the noise level by the adding up the different frequencies that I will discuss later, how to increase the to noise ratio of those things. Okay, so if you do this same experiment repeatedly, then it will take some 30 minutes or 1 hour time. Okay, the time required to get the sample spectra in normal IR spectrometer is very large as compared to FTIR spectrometer. Okay. So in order to resolve this, in order to solve this problem, we have this another technique which is put forward by a mathematician. That is the Fourier transform, and that Fourier transform is implemented into this IR spectrum. Okay. So, what is the principle behind this Fourier transform IR spectrum? Right? We will, for example, if you consider different signal with a different frequency, like you can see from here in this figure A. So this consists of signal with a different frequency. One is this one, okay, this particular signal. Another one is this particular signal. Both of them are having different frequency, so they are different in their phase. Okay, their phase is different. So in if you are considering this point A, they are very in phase. Okay. But in B, they are very much out of phase, and they are in phase like that. Okay, so in this between these 2 points, we can have that interference because when you are having different waves traveling at the with the phase difference, then we can have the interference pattern, and these 2 frequencies will interfere, okay? And we'll get a different maximas and minima. That is the figure 2. Okay, after interference, we'll get intensity pattern like this with respect to time. So all these things are with respect to time. This axis is with respect. Okay, so with respect to time, we have a different frequent intensity because of the action of interference. Okay, and if you consider a wave with some more larger phase difference, half phase difference in those frequencies, then we have a different kind of spectrum. So you can see this this will produce some beating effect here. You can see that, and this beat is repeated in time. So this beat is repeated time like that. So if you consider another two waves with a different phase difference, here we are considering half phase difference, then our beat frequency also will get half. You can see this also we will be getting half of that. So consider, when you consider the previous case, it is up to this point. Only half we are getting as compared to the previous. Okay, so with respect to the phase difference, we will get different uh, reference pattern. Okay, so even we are considering two signals with respect to their frequency, we'll get a different beat structure or beat form. So here we have only two, half of the beat as compared to this particular kind of pattern, which is called as beat frequencies, which is similar to that of the musical notes. Okay. So this is the structure. Now the curve E showing the summation of 5 different sine frequencies. You can see from here in E, we are having the summation of 5 sine waves, different 5 sine waves with the different frequencies. So this E, this particular figure, that is representing adding of 5 different sine waves. Here we are adding only 2 sine waves with a different frequency. Here we are adding 5 different sine waves with a different frequency. So when you are adding up different frequency waves, sine waves, we will get a different intensity pattern because of that interference will happen in that surface. Okay, then when you are adding different signals, we will get different intensity pattern, and the summation after summation we will get a different kind of signal. Okay, and when you are converting this signal by using Fourier transform, then that will produce spectra lines. This Fourier transform technique is a mathematical technique where you convert your signal from time domain to frequency domain. This you might have studied in mathematical physics. So you are converting your time domain function or time domain wave into the frequency domain. Okay. So when you do that Fourier transform, and this Fourier transformation will be done by using computer or a computer system, and all these things will be done by computer itself. So when you do that Fourier transform, for example, in this by using this particular wave, we already discussed that this is consists of 2 sine waves. Yes, 2 sine waves, superimposition of 2 sine wave or summation of 2 sine wave. That will result this particular kind of beat structure, and that if you are converting into frequency domain by using Fourier transform technique, then we will get this kind of spectra with 2 spikes, okay, 2 lines at a different frequency. So these 2 frequency representing that frequency of your initial waves, initial signals. So this is summation of 2 sine waves, and these 2 sine wave have, for example, mu1 and mu2 as their frequencies initially, and when they add up, then we get this kind of a wave or structure for your resultant wave. Okay, the intensity will be varying like this. So initially we have 2 sine waves with frequency mu1 and mu2, and when they add up, the summation will result and like this. Okay, so mu1 and mu2 are the frequency of the initial sine waves. So we will also get here mu1 and mu2 as your frequencies. So we get 2 different peaks at the mu1 and mu2. They are the frequency of your initial sine waves. Okay. So this is the Fourier transformation technique that convert the time domain to frequency domain like this. But in reality, we will never get a frequency like this for any signal. If you are considering any IR radiation, we will not get the signal like this. So if you are having mu1 and mu2, there will be some kind of variation in frequency. There are many different effects that can be possible. Will not get the signal or the this kind of spectra or spike at a single frequency. That is not possible. There will be Doppler effect. There will be temperature dependent broadening of this spectra, and also different physical phenomena are there, and we will not get a single spike at a particular frequency. Instead of that, we will get a little broad spectrum. So instead of a single spike at a single frequency, we'll get a spectra like this with some broadening effect. Okay? So it consists of different frequencies very near to that central frequency, and the maximum intensity will be at that central frequency nu max. Okay, so maximum intensity will be at that position. But along with that frequency, this is maximum intensity frequency at the center. And along with that frequency, we'll be having some small frequency, uh, some other frequency which is less than and greater than that of the central frequency. But they will be having lesser and lesser intensity as the frequency increases or decreases. This is representing a histogram of this particular spectra, and each of these is a histogram lines representing different frequencies present in this particular spectrum. Okay. So then we can see that maximum intensity is at the central frequency. Then these frequencies are having little less intense than that of the central frequency. And again, when you are increasing the frequency, this is getting reduced. This frequency on the sides of that central frequency, their intensity will get reduced. So we will get overall, we will get a spectra like this. Instead of a single spike, we will get a little broad spectra with centered at that particular frequency, mu1 or mu2, and then we'll be having a decreasing intensity that will produce the. This is just a histogram. You have to go in that central position. Actually, if you want to go that, okay, the center of the histogram has to be joined when you draw that curve. This center has to go through this center. So like that you have to. Anyway, so we are not going to discuss about histogram. So that will result in that spectra. And if you are considering any uh, Fourier transformation of frequency into time, then we can also do the same. So the frequency, if you are considering, if you take Fourier transform of this particular signal in frequency domain, then you can also convert that into time domain. That is also available with Fourier transform. So you can transform from time to frequency, or you can transform from frequency to time. Both are possible. If we are considering both, for both we have the equations corresponding mathematically. So Fourier transform corresponding to this, for example, this one single frequency, will get a signal in time domain like this, and it has to be observed that when you do the Fourier transform for this particular frequency, you can get a signal which is decaying with respect to time. Okay? So with respect to time, the signal will be decaying, but the frequency of the signal is constant. You can measure what is the time difference. The frequency is constant in this particular case. So this is a single time wave, but its amplitude is getting reduced while increasing the time. Okay, the frequency is same. So that frequency will be the frequency of the central frequency of the spectrum. That frequency of that signal here in time, that will be central frequency of this spectral line. And but the important thing is that the intensity of this particular uh, signal is getting decreased by increasing the time. So it is getting decayed by increasing time. And so if you are considering same action with a different uh, spectra in frequency domain, then we can get like this. So if you are converting this particular uh, frequency for this particular spectra or this particular spike into the time domain, yeah, just dominant signal from spectral line as it is positioned. So this is in spectra in frequency domain. This spectra is in frequency domain that has to be converted into time domain. Okay? From frequency domain to time domain, you have to consider by using some Fourier transform technique. So this Fourier transform technique will convert this spectral line into a signal like this in time domain, and you can see that signal is decaying and the intensity is reducing as the time increases. And when the breadth of the signal is larger, okay, you can see this breadth is larger as compared to this breadth here. Okay, so when the breadth is going to increase for the signal, which means that if you are measuring the full width at F maxima, if it is larger for this particular spectra, and when you convert that from frequency to time domain by using Fourier transform technique, and then you will get the decaying effect will be larger in that case. So the decay will be larger, and the signal will lose its intensity very quickly. Similarly, if you consider here also, we have changed this. So remember that these two are having frequency at the same position. You can see that both are having frequency at the same position. So their frequency is not changed, which means that the separation, if you are considering separation between these two adjacent signal part, that is, or if you are considering a single cycle, so a single cycle means up to this point, and measure that time period and take inverse of that and measure the frequency. That frequency is same for both these cases. For both these cases, the frequencies are same because we are considering the spectra at the same central frequency, but the width is changed. So when increasing the width, the decay rate will be larger and the intensity of the signal will be getting reduced very quickly when your spectral width is larger. But we are considering same frequency, so the both these signals will be having same frequency. And in next case, we are changing the central frequency position. You can see the central frequency position of A and B figure is almost at this point. It's almost at this point, central frequency of the initial figure. But that has been changed to some other point here, which means that the frequency has been reduced in this case. Okay, so when your frequency is getting reduced and you are converting that into time domain, okay, by using that Fourier transform technique, then you can see now when you are considering this particular signal, consider this one. Okay, so in this one complete cycle, if you consider measure what is the time for this complete cycle and take the inverse of that, you will see that the frequency has been changed in this particular case. The frequency is changed in this case. Okay, so you can see from here. So the time. Okay, if you take this in time, then if you take the inverse of that, then the frequency will be less here. Frequency will be larger. Okay, so frequency will be larger in this case. But I think okay, this also in time, right? also time. So all we are representing, also you have to remember that all we are representing in time. So when you take the inverse of that, which one is having larger time period, that will be having smaller frequency. Okay. So in this case, this is having smaller frequency because this is having larger time period. So when you convert that frequency domain into time domain, in this case, uh, you can see that the decay rate here is also the same as before the first case, okay, figure A. But when you are having the line width which is increased in this case, okay, line width is smaller in this case. So when the width of your spectra is increased, your decay rate is larger in this case because your signal will get the decay and the intensity will get minimum very quickly when your breadth of your spectra is large. So we have a small confusion here because the frequency, when I think when it is moving this direction, the frequency should get, when it's moving, it's not a problem. When it is moving this direction, the frequency is going to get decreased because in this case we have time which is larger, which means that if you are taking 1 by t, your frequency will be smaller. Here the time, which means the time period of the pulse, time period of the cycle of the signal. In this case, that will be smaller. The frequency will be, I think it should be like this. So when we move this side, as in the case of the V number also, when we move this side, frequency should get. Anyway, it is not a problem, but so when you are changing your frequency of signal or the time period of the signal also will get changed in the time domain. When your breadth is increasing, then your decay rate is much more higher, and your signal will get decreased in this way. And here we have two such kind of signal in frequency domain, and we are converting that into time domain by using Fourier transform technique. Then we will get a signal like this. Here also we have that decaying effect, that is the intensity is getting reduced. And when you are having frequency, so this frequency, if let's say this is at mu1, this is at mu2 frequencies, I'm talking about mu frequencies, center frequency at this point. And if you are having this point, we are having mu, instead of mu2, mu1 and mu2, we have, let's say, mu3 and mu4, different frequencies. And if you are adding, if you are converting that into time domain, okay, from that frequency domain, then we get a different spectra. You can see from here. Get a different spectra because the frequency is different. And the decay effect is same because the line width of your spectra is same as before. Okay. Then if you are considering, for example, 3 different frequencies, okay, then we'll get a different frequency spectrum, as you can see from here. And let's say this is mu5, I think this is 6 and mu7, something like that. So they are also different frequencies. If you are adding up all those frequencies, you get different signal in time domain. And we have different frequency here also. Let's say this is some different frequencies mu n. You have to consider different frequencies, and we have different kind of in time domain. So that means that what we mean by using this is that we will get a different time domain spectra, different frequency domain spectra. Correspondingly, if you are having different spectra in your layer. So if you are having three different spectra, when you convert that with using Fourier transform signal, you get a different signal in time domain as compared to 5 different spectral spikes or spectral lines in your frequency domain that is converted time domain. So the frequencies will be enabled. So in FTIR spectrometer, what we'll do is that we will be having sample in this position, and we send all the signals at the same time. Instead, in the conventional spectrometer, we will evaluate for each of the frequencies separately. But in this case, we'll send all the spectral frequencies at the same time into the sample, into a single point, and will be having interference at this point for this sample. Okay, and we will take the interference. After interference, we will take. Actually, this will be in that mirror. Sorry, this will happen in that mirror. I will explain in that next class. So this will happen in that mirror, and this interference, after this interference, this signal will be passed through into the sample, okay, to the sample, and then it will go to the detector. It will go to the detector, okay, detector. And this detector will detect which are the frequencies which will be absorbed and all this. And the remaining things will be coming to this system. Okay, and okay, this actually this detector I think also is directly going to the system, and the system will detect which are the frequencies in there. This so this frequency, which is a superimposed uh, signal of all these frequencies. So this will be like this. That, for example, like this, a different, very complex signal will be. This one will be very complex signal. So this one will be like very complex like this, because it is having different frequencies superimposed with that. So we have a complex signal here that is going to be that is going through the sample, and some of that frequency will be absorbed, and this one will be again some complex frequency, okay, something like this, and that will be coming to this system computer, and that will be stored, and we will take the Fourier transform of this signal, and we will get a spectra, which is having that frequencies. What are the frequencies which are present in this particular spectra after taking that Fourier transform? Yeah, then we will get if you are taking it for all these lines, then we will get something like some lost something, and we will get this IR spectra, Fourier transform IR spectra. So this is a rough introduction to the Fourier transform IR spectroscopy. We will go to into the detailed explanation. So this is a rough introduction of the FT Fourier transform IR spectroscopy. This is a little tricky or little difficult to guess, but this is the basic principle behind that. We have to convert that frequency into time domain after taking all those interference and time from time to frequency we have to convert, and that we will represent in terms of centimeters. So we already discussed some basics of the introduction to that FTIR spectrometer, and today also I will get some more points. So we discussed about the Fourier transform technique in the last class, and in this FTIR spectrometer, if you are using this Fourier transform technique or this FTIR spectrometer, here we use the computer, okay, unlike the conventional IR spectrometer. So computer will store all the data which will be received from the detector. Okay, so that is the first thing that we have to understand. Computer receives all the data from detector. Okay, so computer will get all the data from the detector. So detector means we will be using photo detector, or we can use that cells, okay, which will measure that pressure difference, correspondingly it will measure the temperature, and that will be plotted as transmittance. So any of those detectors we can consider, and from that detector the computer receives the data. Okay, what is the current at a different or in the program we have to consider. In this case we cannot distinguish each and every frequencies because we are not using monochromator in FTIR spectrum. I will discuss that in later sections. So we will be sending all the radiation at the same time, and all the radiation will be passing through the sample. Like after that interference and all those things, we will be having signal with a different intensity pattern, and that will be passing through the sample, and the detector will detect the different frequencies or intensity patterns in that sample. Accordingly, that will produce the photocurrent, or that will produce the temperature differences, and that will be passed to the computer, and the computer stores all those data in n number of large number of space. Okay, this computer receives the data from detector and stores the data in large or many memory locations. And this data then, what is this data? This data will be in time domain because we are sending all the signals that is in time domain. It is varying with respect to time. So all the signals will be stored in the memory of the system, this computer, and it will use thousands of memory space for this. So it is not like a single memory which is using memory location. It will be needing thousands of memory locations corresponding to each and every points which is received from the detector, corresponding to that intensities corresponding to different frequency combinations. So basically it will be an interferogram. So what will happen if you are sending all those frequencies? We will get an interferogram with a different kind of uh, signal pattern, okay, something like this. And this interferogram will be going to the sample. So this interferogram consists of n number of frequencies, different frequencies. They are combined together. They are superimposed together. Okay. So this will be going to the sample, and that after absorption of some frequency by the sample, that will be coming to detector. Okay. So in detector, we will be having some different kind of frequency spectra. Okay. And this spectra will be going to the computer system, not the spectra. The intensity associated with this intensity, we will be getting. For example, your spectra is like this. After that sample, your spectra is like this because some of the frequency will be absorbed by the sample, and the remaining is like this, for example. So let's say this is your frequency. It will be very complicated signal because we cannot understand because it is an interference of n number of frequencies. So this will be very complicated signal, and this signal will be given to the detector. Okay, and what is that detector? So this is with respect to time, it is varying. The signal is varying. So the detector will detect with each time what is the intensity. Each time what is the intensity. Each time what is the intensity. So it will be detecting like that. Okay, each time what is the intensity of the signal. Okay, so and that information with respect to these intensities at a different time, we will be getting different current corresponding to this each of this time interval, because the photo current depends on intensity of the incident radiation. So incident radiation will be having different intensity at different time. Okay, and that will be detected by the detector if you are using photo detector. So that each time this intensity corresponding to the intensity of this signal, we will be having current. For example, in this case, let's say we have current of 5. I'm just talking about the magnitude. I'm not talking about unit. Okay, so this is 5 again. This is 5 again. Then we have an increase. So this will be some 6, 7, 8, 9. Then it is coming back into 8, and then somewhere, then it is going to some 7, then some 6, then let's say this is some 7.5, something like that, and then it will again go 7, and then it will go again 8, 9, 10. Okay, I'm talking about this speed. Yes, so these are the current produced at different time interval, time in seconds. So we have to take the detector also will be detecting in a very short interval of time. So this is 9, this is 10. So all this time the current will be produced and the magnitude of current will be different with respect to that intensity. Okay. And this current which is produced at the detector, this current will be uh, given to that computer system. Correspondingly, with this current, the system will be storing this data, this information, this current which is produced. Correspondingly, some magnitude will be stored as data in the computer system. And that computer system, after storing all this data in time domain, this will be converted into frequency domain by using this Fourier transform technique. So if it is the detector is detecting 2000 time interval, if it is detecting the current at the 2000 time points, if you are dividing the signal into 2000 time, and then the correspondingly the uh, the this system also requires some 2000 memory locations to store all these data, and all these data will be in time domain. Okay, and that will be converted into frequency domain, and correspondingly when we convert that into frequency domain, each frequencies in this particular signal will be uh, resolved by using this Fourier transform technique. So then we will get different peaks at different frequencies. Okay. So basically, we store all this data in computer system. Then we do the Fourier transform analysis of these data. Then we get the frequencies at different positions in that frequency spectra, frequency bands, and correspondingly we get the IR spectra for the sample. So that is the basic operation. So in order to store all this data, we need some large space in the system. And if you want to do some repeated experiment for the same data, because in some cases some noises can be present in your data. So I will move this part. Because this is, let's say this is so let's say there is some noise here, for example, in this particular case, some noise. So it is not present in this side. So some noise, sometimes noise can also come in within the signal. So if you take the same spectra next time, that noise may not come. Okay, so if you are taking the same spectral analysis multiple times, so the noise which is coming from other some scattering or something else, that can be avoided. Okay, so if you take the spectra of the same next time, okay, one more time, if you are taking the same spectra, let me see if we can copy this. Possible. And, cannot be possible. Okay, I will just draw that in here. It will not be same. Okay, so it is almost. Anyway, am talking about the same spectra. So next time also we'll get same spectra, and if in that case this noise may not be there. If you are considering this as our noise, then that noise will not be there in the next time. Okay, when you're doing in the repeated form. Okay, so in that case we will get the same spectra without noise, and these two we have to add. When you add these two, then we'll get much more intense spectra with these two. So, for example, we get something like this. Okay, the same spectra, but the intensity will be a little larger. Okay, so intensity will be increased. Let's say this is at intensity of 5. This is at intensity of 6. Now what will happen? We will be having very small spike here because of that noise. This noise. That it is there in the first spectrum. So if you are considering that, we will be having more here because the intensity of the total spectra is increased. Okay, I will not draw that in that position because that is noise. So that noise will be somewhere here. So because sorry, somewhere here because it is intensity is at some 5. So we cannot take that. So its intensity is now very small as compared to the signal intensity. So this is just like a flat. So, and we'll be having the noise at this point. And if you consider large number of such if you are considering large number of such signals, such patterns, then we will be having very low intense noise here. Noise will be very low, and we do not have to consider such kind of noise because the amplitude of such noise will be getting reduced, and only we have to consider this signal. Okay? So if you are taking multiple observation or multiple examination of the same signal and adding all the signal together, that will reduce the noise level. Okay? Because the intensity of the spectra will get increased each time. Okay, in like this, okay, and the noise will be getting reduced. This is difficult to understand when we talk about the signals, but when you talk about the spectra itself, if you are considering that spectra in case of spectra, Normally we do that in by using the spectra. Okay, that's why going to this spectra. After converting that into spectra, for example, it is I will draw that much more simpler way because I have to draw it again. So, for example, if you consider a spectra like this, okay, and there is some noise here, okay, because it is coming from some scattering or something. So this is in frequency domain because this will be much more easy to expect. Yeah, this is in frequency domain. So the computer will be analyzing that the time domain and converting that into frequency domain by using Fourier transform technique. After that, we are adding that signals. Okay, so this same experiment is repeated, and I am getting same kind of signal, same kind of spectra. Okay, uh, in frequency domain in the next time also. And in that case, we will not be having this uh, noise because noise comes randomly, and the scattering of some other physical phenomena associated with this noise may not be present next time, and it may not be present at this same frequency. So next time maybe some small noise may be present at this position. So if you add these two signals, what will happen? If you add these two signals, you will get a very large peak at this position, initial position, and then you will have a very small spike because of that noise. Then we have again very large signal at this position, and then again we have this width will not change much. Spectra will not change. So we'll be having the same kind of width, and the intensity will be getting increased, and then also we will be having very small noise at this position, and then we'll be having very large noise. So what is the advantage of this taking the same experiment several times is that we can add up those intensities. When you add up all those intensity, our noise level will be getting very small. Okay, these noises will be getting very small as compared to the original uh, signals or the spectra which we need. Okay, this amplitude will be as compared to the noise. So then signals to noise ratio will be getting reduced in this case. Okay, so if you add these two, you will get it like this. So, but this is possible if you are using computer system. Otherwise, you cannot add two signals after in that frequency domain. We can examine that in frequency domain. We can get to the spectra for a uh, single examination or single transfer of this IR spectra. That can be done, but we cannot add up all those signals. That addition of different signals is possible only by using computer. And this particular technique is called as computer averaging. Transient. So this is the technique, computer averaging transients, where we will add up all these signals by doing the same experiment twice and twice or many times in order to reduce, this is doing in order to reduce the noise. So this technique is computer averaging transients. So if you take scan, if you take n scan, that increase the noise level by n scan increase noise level by n to the power 1 by 2. That is its rate of increase will be very small. And the S by N ratio, if you take, will be, if if you're considering n scans, then you have a signal of n. So signal to noise ratio we have to consider. So n samples or n scans we are considering. So it will be having signal strength of n and n raised 1 by 2 is the noise. So the signal to noise ratio will be, this is just a calculation, but this technique we have to understand. Okay? This technique we have to understand. So this technique is called as computer average transit, and this is possible only in the case of FTIR spectrometer, where we use computer averaging and computer manipulation. And this is also an advantage of FTIR spectroscopy. We will discuss about the advantages. So this is possible by in the case of FTIR spectra. Also, the removal of the signal also same in the same procedure, but there we will subtract one signal from another signal. As we discussed before, if you are using solid sample with paraffin oil, if you want to remove that paraffin oil petrol lines, then we can do that also if you are using the computer system and decrease each and every points from the combined spectra corresponding to that paraffin oil and the spectra corresponding to that solid. For that is, for example, I will just show that. For example, if you are having spectra like this, okay, and this is, for example, corresponding to paraffin oil plus sample, solid sample. And if you are having paraffin oil spectra, this is just a rough diagram. I don't think that it is exact of the paraffin. It's just a rough sketch of this. So if you have the paraffin oil spectra, this like this position. Okay, so this is only paraffin oil. So this has to be subtracted. So this is paraffin plus sample, and this is paraffin oil. So computer knows each and every intensity at at the different frequencies. So this is in frequency domain, and this is also in frequency. Or it can be in that wave number. So okay, so also that in wave number. So both of them are, we usually do that in centimeter. So in all figure you place that. Okay, that is also possible. So anyway, this has to be subtracted. Okay, so computer knows the paraffin oil. If you are already know that paraffin oil spectra, and if you fed that into the computer system, then computer know with each of this wave number what is the intensity corresponding to this paraffin oil. Computer also have the data for the paraffin oil plus your sample, and it is stored, it is converted into frequency domain, then it is converted into wave number, and which is like this in the case of first figure. And each of the for each of this centimeter inverse or wave number, computer knows what is the intensity when you are having paraffin oil plus sample, because all the data is stored in the computer system. So you have to subtract some numerical values, some intensity. So a computer averages these values into maximum of 100% if you are measuring that transmittance, and the maximum value will be 100%. You are considering that, or absorption if you can consider. So I'm talking about this. This should be absorption. These fans are absorbed by the sample. So absorption, absorption. Yes, absorption is minimum here, which means that the transmitter. So that maximum will be 100%, and the remaining will be less than that. So computer will be normalizing. For example, for 100%, it will take value 1, and correspondingly, for other intensities, it will take value 0.9, 0.8, etc. So different values will be stored corresponding to those intensity of a different wave number position, and that is plotted as your spectral line in terms of percentage. And similarly, we will be having paraffin oil, and corresponding to that spectrum also we have different values, 1.9, 0.8, like that, for different frequencies in between 1 and 0. And that we have to subtract from this main, that the spectra of paraffin oil plus sample. So what will be the result? The result will be, that will implies we have same kind of spectra at this frequency position. This is same frequency because of my drawing. It is shifted a little bit, so that we will get a 0 there. We will not get any spike at that because we are subtracting same intensity. And then we have coming, and we will be having frequency at this position, because paraffin does not have a spectra or frequency this position. So we will be having that spike. And in the next, we have a very small spike in the. So here also we have this this particular spectra, which is also present in there. And then the next one, which will not be present because we have the spectra, this particular band at same frequencies with same intensity, which is associated with paraffin. When you subtract that, you will not be getting that. Then we have to go to the next line. This two will get cancelled because the same intensity at same frequency. And we will be having some small signal in this position, because we are having very large signal at this position, some small here with the paraffin oil. So the same vibration present in both sample as well as in the paraffin oil. So some portion of that is coming from paraffin oil, some of that intensity which is coming from the sample. So when you subtract that, the total intensity will get reduced, and this is coming from the sample. And then we have the other spectra also, which is coming from sample. Okay. So almost our spectra will look like this after subtracting spectra of paraffin oil. So this is the sample spectra corresponding to that sample. So this also can be done by using the computer system. So by using the FTIR spectrometer, we can do all these kind of subtraction addition, which will not be able to do in the case of conventional spectrometer. Okay, so by using this technique, we get the spectra of sample after subtracting that from the paraffin oil. Okay, so that's all about today's class, and in the next class we will take the FTIR spectrometer, and we'll discuss more about how we will convert. Conversion is the Fourier transform. I will not be talking about that because it's a mathematical process done by the computer system itself. But we will discuss about how it is working, how we will use the program in the microsun interferometer, spectrometer, all those things. And then we will move to the FTIR spectrometer, and this is a representation of the same, but here this figure is taken from your textbook. Okay, let's reduce this size. So this is taken from your textbook. This is the IR spectrometer, and you can see from here there are two mirrors, M1, it is M1, and this one is M1, and this is the M2 mirror, and this M2 mirror is movable or adjustable, and this M1 is fixed. M1 mirror is fixed. This one can move this longitudinally in this diagram. Consider this diagram, it can move in this direction. Okay. And the IR source will be this enhanced filament, or we can use enhanced filament normally. Okay. And then that IR source, from that filament, the radiation will be coming out. It will be reflected by using any KBR or NaCl mirror. And then we have to pass those IR radiation through this B. Okay. And this one will split the radiation into two different direction. Half of it will be passing through this, and then half of it will be passing through this direction. So half of the radiation will go to mirror M1, and half of the radiation will go to mirror M2. And it will come back after hitting on those mirrors, and it will reflect back, and this from this mirror M1 also it will come back, and that radiation will be intersecting at this point. Similarly, those radiations hitting at this point, this part of the B, yeah, that will be again intersecting at this point. Okay. And this I will explain more about this components in the next figure. I'm just giving just a rough idea. So this is similarly there will be a large number of radiations will be coming and hitting these mirrors side. Okay. So all those radiation will be coming back and joining at different points. This B, and then similarly this is 50 percentage in this. We have 50 percentage of transmission and 50 percentage of reflection. Okay. So when it come back, also some 50 percentage of that radiation will be going to the source. Okay, but that we do not have to consider in this particular scenario. We have to consider those radiation which is coming down after intercepting in each of these points. So this radiation will be going to sample and detect. So I will explain that again this diagram. Okay. So this is much more a better diagram. So in this case, we have the source, IR source here. You can see that this is our IR source, and the IR radiation will be coming like this. Okay. So when it reaches at this point, half of it will be reflected to this mirror, moving mirror, and half of it will be reflecting to the fixed mirror. This I have taken from my channel. Yes, that is it is some lecture from IAC. So this from this point, half of it will be reflected to this moving mirror, and half of it will be passing through this beam splitter. So this beam splitter will be splitting this particular beam in such a way that 50% will be reflected back and 50% will be passing through. Okay, so 50% will be going like this, reflected to this mirror, and 50% will be transmitted through this beam splitter. It will reach to mirror M previously. I think it is M2. Oh, sorry, this is M1 and this one is M1 and in mirror is. Okay, so then after reaching this M1 and M2, these IR radiations come back, okay, and they will intersect at this point. Different color here. So the reflected IR radiation from this mirror as well as from this mirror. So this is for just a representation I am showing. That reflected beam also will be coming from the same point. If we are considering this is the transmitted IR radiation, then the reflected will also coming in the same direction back to that point. But let's consider some other radiation which is coming back after reflection. So that radiation will be meeting at this point, and this from this mirror also some radiation will come, and that also meet at this point. So as we discussed, the beam splitter will split half of the radiation in such a way that half of the radiation will be transmitted and half of the radiation will be reflected. So from this radiation also half will be coming in this direction. From this radiation which is coming from that mirror M1 also transmitting through this beam splitter, and they will come towards that source. So that we are not considering. Then only considering those 50% which is transmitted from this radiation which is reflected from M2, and 50% that is reflected by the beam splitter from this radiation. So actually what is happening is that the reflected radiation, IR radiation from M1 and M2, they will intercept at a point, okay, in this beam splitter. That is the important point. So when they intercept, as we know, when two radiation intercepts each other, they may be having same they may be in space, okay, so they may be in phase like this. If you are sending a single radiation to this beam splitter, then the reflected wave, let's say, I think it is better to use some notation. Let's say this reflected wave, this transmitted, that is from source, whatever we are sending, that is, let's say, one single wave. Okay, in this case, we are considering only one single wave. So one single one radiation with one particular wave. So if you are considering like that, let's say that is X which is coming. Okay, so this is X1 that is going towards the mirror M2. Oh, so this is, let's say, X2, because we are already taken that M2. So better to use X2, and this one is X1. Okay, so that those radiations are going towards the mirrors, and let's say this is Y1 which is coming back from the mirror, and this is Y2. So if you are using a single wavelength from your IR source, you are using one particular wavelength, let's say 1000 let's say 1000 nanometer. Okay. So in that case, you are using only one particular wavelength, which means that those radiations will be coming back from the mirror and intercepting at at a point in the beam splitter. Since they have the same wavelength, and they are in, if these mirrors are adjusted in such a way that this distance covered by Y1 and Y2 from that intercepting point towards that mirror, let's say that is constant. Distance between the beam splitter and M1 and the beam splitter and M2. Let's say they are same. Okay. If they are same, then both of these radiations will be in when they reflected back, they will be in phase. So basically, uh, when the M1 and M2 mirrors are at a distance, constant distance, which is same from the beam splitter, and we are using single wavelength IR radiation. So because of this, those radiations which are coming back after reflection, that is Y1 and Y2, they will be in phase. So we can say this is Y1, this is Y2. So when they meet at the beam splitter, actually what happens, these two beams will be adding when they meet at. That's why we are using this mirror and this beam splitter setup. This is nothing but an interferometer. So this interference will happen at that point where this Y1 and Y2 join. Okay. So what will happen? Since these two waves are in phase, constructive interference will happen, and we'll be getting intensity pattern which is more higher. So we'll get intensity which is more higher in this phase. So like this, the intensity will change. So this is the pattern after that interference. So this is the basic principle of that interferometer when we are having when we are dealing with a single beam. Okay. Now, if you consider if you are varying this M1 and sorry, M1 is fixed, we cannot change that position, that mirror distance from beam splitter. But M2 can be varied. This M2 can be varied, which is the moving mirror. Okay, this M2 can be varied in this direction. So if you change that M2 position, what will happen? Y1 radiation will see some path difference. Initially, you are having this both Y1 and Y2, which are in phase because there is no path difference. The distance from beam splitter to M1 distance from beam. There's no path difference in the interferometer. So both will be constructively interfere. So both will constructively interfere when we get a very high intensity and low intensity. But when you are considering the motion of the M2, that is, if you are moving mirror M2 a little bit, which means that you are changing the distance from beam splitter to mirror M2. In a different way, you are making an additional path difference in Y1 radiation. So Y1 will be having some path difference. So this Y1 and Y2 are no longer uh, going to be constructively interfered. So in some point it will be destructively interference will happen. So that we'll discuss. Okay, so before that, I will discuss the components of this IR spectrometrology components. So this is the IR source that we already discussed, and this is beam splitter, which splits the IR radiation which is coming from the source into 50%, and some passes through to M2 and some passes through into M1, and that join at the beam splitter. And those radiation which joined at the beam splitter will be coming towards this direction. So that will be reaching at this mirrors. All the mirrors are KDR or NaCl. And then they will be coming to this sample. So this is some gas. There's some gas in and out. So this is the cell that we already discussed during the sampling technique. So this is the sample, and this is nothing but some gases, gas molecules are there. Multiple reflection will occur in this particular gas chamber. Anyway, so this is not chamber, this is long. So multiple reflection, and this IR radiation will interact with these molecules inside, and we'll get some IR radiation will be absorbed by the molecule, and the remaining radiations, which is not absorbed by the molecule or the different branches, the different groups in this molecule, they will absorb the radiation and vibrate inside the sample. If they match with vibration frequency, then the remaining frequencies will be coming back, coming through this mirror, and it will be detected by this IR detector. It can be by photo detection method, or it can be by temperature sensing method, and then it will be going to the computer system for the Fourier transformation and further spectral analysis. So these are the basic components of IR radiation. Sorry, IR FTIR spectrometer. Now we'll explain those concepts with the moving mirror. So we have this fixed mirror here and moving mirror M2 here. So this is M2. This is at different position. This must be lambda by 2, lambda by, this is 0. It's lambda by 2, then this one. Then we have lambda by 2, then we have 3 lambda by 2. 0. This lambda by 2. So 0 lambda by 2, then lambda, 3 lambda by 2, then we have 2 lambda. So okay, so this is your IR source. IR source here. IR source. This one is IR source. Okay. And as we discussed, the radiation will be falling on this mirror and it will be coming to this beam splitter, okay, like this. Already discussed that in the last video. Okay. So those radiations will be going through, and some of them will be going to M1 mirror, and some of them will be going. And we are focusing on this M2 mirror. What will happen when we move that mirror to different? And this is also lambda, lambda, lambda. I think it should come like lambda. Because we will be having constructive interference at the lambda position, which means that it should be zero, that the path difference or the phase difference should be zero, or it should be lambda. The path difference should be 0, lambda, 2 lambda, 3 lambda, like that. So n lambda. Then only we will be having constructive interference. If it is lambda by 2, n lambda by 2, then it is destructive interference. You can check that. So for constructive interference, we have, for constructive interference, we need n lambda. It can be 0 also. And for destructive interference, destructive case, we need n lambda by this path difference will be n lambda by 2 for destructive. So what will happen in the first case? So I'm not going to write any notes in this section. I will explain each and every steps and everything. You write it and read the text because it is very lengthy to explain itself. So this is the first position when lambda is equal to 0. Let's say this is 0th position. So in 0th position 0, we have the mirror M1 and M2 which are having the same distance. So this is not at the same distance in the figure, but let's say this is these two are having same distance. This one from that center of that figure, we have let's say this is this x distance, and this one also will be to this mirror I'm seeing x distance. So both these mirrors are at x distance, so that the path difference between mirror one, this radiation which is coming, it will experience a path difference equal to 0. Okay, because both the distance between M1 and the mirror and M2 and the which are same. So since they are same, their path difference experienced by this radiation will be same. Means that it is 0. Okay, so path difference will become 0, and so when the path difference is 0, they will constructively interfere, okay? And we will get a maximum. We'll get a maximum intensity corresponding. Now, when you consider lambda by 2 position, that is position 1, when you consider that the mirror is moved with the lambda by 2 distance, that is M2. M2 is moved with the distance of lambda by 2. So now we have x distance from beam splitter to M1 and x plus lambda by 2 distance to M2. Okay. So the distance in the direction of M2 has increased by lambda by 2. So the path difference experienced by the radiation which is coming back to the beam splitter from M1 and the beam which is coming back from this M2 to beam splitter, that will be different. That will be lambda by 2. So the path difference now it will become lambda by 2 because we are moving the mirror M2 by a distance of lambda by 2. Okay. So when the path difference is lambda by 2, we have this condition and lambda by 2, and the interference that will occur at this point when we come back will be a destructive interference, and we'll get a minimum intensity. So they will cancel each other. basically they will cancel each other because they will be just in the opposite because we have a lambda by 2. So if you consider one as a sine wave, so if you are considering sine wave, okay, then you will be getting a cosine wave from M2 because they are destructively going to destructively. Uh, then it is going down. So here it should be maximum. Here it should be minimum. Right? Here and here. Point. Actually, they should cancel, right? Because there will be a lambda by 2 phase difference, and then we will get the destructive interference with the minimum intensity. Uh, just check that diagram. Okay. So anyway, so this is the condition for that destructive interference, and this will get minimum intensity at this point. And then again, if you are moving this particular mirror, and then for example, next time it is going to be at lambda position, then we will be getting a maximum intensity at lambda. Then we will be getting 3 by, if it is at 3 by 3 lambda by 2, have again destructive interference, and we will be getting at 3 lambda by 2, or it will be destructive at that point, and that continues. So that so each time we have this interference which will happen at this with respect to this. So this will form a cosine wave. So you can see that the intensity variation is like a cos wave, a cosine function. So with the mirror moment, M2 mirror moment, we have a cosine like intensity variation. So this mirror will be moving as a total. It will be moving in centimeter 1 centimeter. That, but within that 1 centimeter and 2 centimeter, it will be covering like with a fraction of some lambda by 2, some very small value. Okay, so within 1 centimeter, it is going to cover, for example, within 1 centimeter, it is going to cover some thousands of different positions. Okay, so total thousand number of values or number of points we have to store in the computer system when it moves, when the mirror M2 moves within 1 centimeter. So within 1 centimeter, it will be moving very slowly, and that will be controlled by some particular system, okay? Something with air controlled system. So that will control the motion of M2, and that M2 mirror will be that will be moving in a very frictionless manner. So only that air will be there inside, and that will adjust that position of this mirror. And also there will be very small friction. That will be like a frictionless movement type. So the M2 will be moving very very smoothly, and so once within 1 centimeter, it can take thousand number of positions. So the variation of the M2 will be very small, and it has to be in different points within 1 centimeter, different thousand points. So you imagine that the motion of M2 will be in very small. So it is, we can say, infinitesimally small. So it is that much of very small. It will cover in each time distance it will cover. So and correspondingly, the path difference also will be having that in terms of this lambda by 2. So we'll be getting some interference of the radiation which is coming in this range. Okay, so within 1 centimeter, if it is moving, M2, if it is moving, then it will cover, it will be positioned in thousand number of points between that, in between that one, which means that if you consider 1 centimeter, and if it is covering 1,000 1,000 points, so 1 by 1,000 we have to consider. So this much it will move in each of these steps. So this will be, what is this value? This much. So it will be moving with 0.001 centimeter. So like that it will move. So the variation, this much of steps, this much of centimeter, it will move in meter. So the variation will be very small, that M2. But sometimes it may be much more smaller than this value also. So it will make this interference pattern. And that interference pattern we already discussed in some other classes before. So that I will show how it is coming. So if you are using, you can see here, if you are using a single beam, yeah, then you will be getting a pattern like this. It will always start from cos wave, that is maxima, and then it will go to minimum, and then again maximum. And you can see that the intensity is getting reduced. So this kind of interference pattern that we can observe from that because of that movement. Similarly, if you consider, so this is just a transformation, Fourier transformation. This is the variation of time domain signal from a spectral line as it is position and breadth wave. So this is just, when we discuss the Fourier transformation, we talk about these things. So you can see these variations. And if you are using two different frequencies, what will happen? For example, if you are using two different wavelengths, now there are two things that will happen in this case. Because when you are having two frequencies, mu1 and mu2, these two frequencies will interfere because they will be having different. So they are having lambda difference in there and phase. So they will differ the movement of M1 and M2. then we will get a very complicated spectrum because we have both in. So interference of mu 1 and mu 2, we will get this kind of uh, structure with the beats, different beats, beat structure you can see. And then along with that, we have some kind of cosine spectrum radiation. If we consider that intensity, we have to consider total. Okay. So we have to consider from here, it will go like this, come back. So you can see that pattern also here. Along with that, we have that interference with mu 1 and mu 2 if you are having two frequencies. Similarly, if you're having three frequencies, then we have a different kind of pattern like this, uh, along with that cosine variation with the intensity which is. So this in this case also we will get that pattern. So that is the action of mirror as well as the different frequencies which are coming and interfering in this picture. So in FTIR spectroscopy, we will not send one particular wavelength at each time. We will spend all the radiation. We will be having this moment of sorry, this mirror M2. Okay, in that case, we will be having very complex spectra in that particular case, and that spectra will be going to the sample. Okay. So those spectra will be going to sample, and some of them will be absorbed by the sample. Okay, and then the remaining spectra will be the remaining radiations, radiation will be going to the detector by using that photo detection method or that temperature detection method. We can measure what are the radiation which are coming, and those detected radiations will be feed to this computer system. And for example, if that mirror moved with some 1,000 points, 4,000 points within 1 centimeter, let's say, in such a way that it is starting from 0, then it is going to 0.001 centimeter, then to 0.002 centimeter, like that. If the mirror is moving, then correspondingly we have different path difference, and we have different kind of interference pattern that we okay. So correspondingly, so if it is moving for 1,000 points, we have to store all these 1,000 points in that system, in computer system. We have to store all those 1,000 points. If it is scanning for 2,000, then we have to store all those 2,000. Okay. So all those values will be stored in the spectrum. Okay. And the spectrum, in the system, and the system will be uh, analyzing those points, 1,000 number of points, and from that it will convert that this number of points. That is so as we discussed, we'll be having very complex interferogram, okay, which is coming to the sample, and the sample, when it is reaching at the sample absorbs some of these frequencies, and the remaining frequencies will be coming to the detector, and the detector will be um, storing all the points inside this system. The detector will be giving that data into the system, and system will store all those points in its memory location. And correspondingly, then it will do that Fourier transformation of that particular spectra or radiation with respect to this is varying with respect to time. So that will be converted into frequency domain, and we will get corresponding frequency spikes. That is the system will convert all those things. and then we'll get the transmissions or absorption. Okay, so this is the technique, basic technique that we'll use in IR spectroscopy. So this is the basic idea behind the IR spectrometer, and the Fourier transformation is a mathematical process that use from the time scale it will convert that into frequency scale or frequency spectra. Sorry, frequency. So that conversion, I don't. That is you. I have scheduled that. Okay, so that's all about FTIR, and also the if you check the resolution is nothing but the suppression or the ability to separate each and every frequency component. That is the resolution of IR spectrum. So we can say that it's nothing but delta mu equal to mu1. So if you are having two bands within here, and if you can separate that, then how much you can separate the solution of your IR spectrum. So it is nothing but the ability of this to separate two spectral speech is associated with the spectra. You can separate it out from two different types. In case of FTIR spectrometer, we can also define that as 1 by delta max. Is also equal to 1 by delta max, which means that resolution equal to 1 by delta max. So the delta max is nothing but the distance of this. So we will be getting this figure I have just shown to as a representation to this as a representation to that cosine wave. This is the basic principle of. Now, if you want that, okay, that cannot be needed. You can look at into that the Fourier transformation from frequency to time and time. There are two equations, which is measured. So okay, so normally the observed signal at the detector is a summation of all these cosine waves. Okay. So this gives maximum at the Z. Zero position. Okay. This position. Zeroth position. If you consider this zeroth position, so for each wavelength, for example, if you consider for each wavelength, we will be getting this kind of a pattern, right? So what is actually happening here? For example, if you consider this zeroth position, we'll be getting a pattern like this. And in the next case also, we'll be getting a pattern like this. For example, if you consider some other wavelength, which is also having this kind of interference pattern. Okay? And but this lambda by 2 and all those things, if you are considering, that is going to change because their lambda will be different. Well, understand this concept very well, then it is easy. Because this particular FTIR spectrometer, we cannot get that much clear picture in a single or single video. So you have to look into deep because it includes the different components. It includes the basic physics. It includes the technical part. It includes the computational part. It includes mathematics. So it's a wide topic. But in order to understand, we have to, in order to study in a capsule, and we have to look into this. So, for each wavelength, we'll be having this kind of a cosine. Okay, that is, I hope you understood this point. So, if you are considering any cosine wave, any of the cosine wave, sorry, any radiation with lambda, I will just explain it here. So, let's say one lambda, one particular wavelength which is coming from the IR radiation, hitting on the beam splitter, splitting and coming back to this beam splitter again after hitting on these mirrors with the zero path difference, giving you maximum intensity. Then we are moving the mirror. We will be getting maximum, minimum at lambda, maximum at lambda. All this happening, and you will get a cosine wave like this. That is for one wavelength. Now, if you use a second wavelength, for example, mu2, if you are using mu2, what will happen? You are getting two frequencies. You are using two frequencies, two different IR radiations with the two different wavelengths. Okay, so now we will be getting a different cosine wave. Okay, so all of them will be having. I will just increase this size of this particular figure so that I can draw that in. Because understanding this, the concept is very I'm just explaining how we get that pattern. So if you consider the second radiation, let's say it is having a a little higher frequency than the previous wavelength. Okay, so in such a way that mu1 was first frequency that we considered, and we get this kind of a spectral interference pattern, and then we have let's consider mu2 second one. So in such a way that mu1 is less than mu2, so mu2 is having frequency higher frequency, which means that their lambda will be smaller. Okay, so if you are considering uh, this is your lambda by 2, and this is your lambda, this is your 3 lambda by 2, etc. This is your 2 lambda. So in this case, what will happen? This is your 0. So in the second case, I'm saying that for mu2, we are having lambda which is less than mu1 because it is having a higher frequency. So since lambda is smaller, in the next case, what will happen? So the maximum will be at this position at 0. There is no difference. So in next case, it will be coming somewhere here because lambda value is smaller. So lambda by 2 value will be also smaller. So it will be coming and reaching at this point. Then it is going like this. Okay. From here it is starting reaching somewhere here maximum, and then it is coming back. Okay. So for this radiation, these lambda positions will be different, and we will be getting an interference pattern like this. In this case also we have a spectra. So this is for the case when mu2 is less than mu1. And another frequency, if we consider mu3, which in such a way that which is less than mu3, uh, mu mu1 mu1 in such a way that mu3 will be having lambda which is larger than mu1. Okay, so from that mu1, this one this lambda will be larger, and that particular uh, for that particular frequency, the intensity pattern will be coming like this because it is having larger lambda. It will be falling somewhere here, okay? And from there it is going again like this, and it will be having here and then back position. So it will be going like this. Okay, so for different frequencies, we will be getting different interference pattern like this with the movement of that wave. Okay, now if you take a summation of all these, this is only for the case of three different frequencies. Now, if you take summation of these three, for example, yeah, this is for three frequencies, then we will get this kind of a spectra that if you are considering three frequencies, then so let's consider this one, three frequency with three frequencies. So we get this kind of a spectrum with this three frequency combined together. We get complicated spectrum. This is only for the case of, so you can see that maximum will be always at the initial position, then the intensity will get reduced because of that interference that is happening, because that maxima and minima will be different at a different position. Then we have to add up all those points. We'll be getting a complex spectra. So each time from there onwards, we'll be getting different maxima and minima position. But overall shape will be like a cosine wave. That intensity shape will be like cosine, because always that maxima at the initial position, it will be having maximum intensity, because all the radiations interference pattern will be starting at the starting with the zero path difference, will be having maximum. So in that case, all of them are having at the same intensity at the zero position, which means that when there is no path difference, the intensity is maximum for all the radiations. So when you combine all the radiations interference pattern together, we will get a maximum at the zero position when you are having, if you are considering. Then that it will be getting reduced because we'll have different uh, intensity at different point, different wavelength point positions. So uh, then we'll be having different frequencies at different positions, and we'll be getting very complicated interference pattern, because when you are considering this one, we are having maximum intensity at this point. Then we will be having some, for example, if you consider this point. So for this mu2, we are having minimum intensity, okay? And then for this mu1, we have some intensity somewhere here. Then this mu2, mu3, sorry, this one is mu3, right? So this mu3 also having some intensity. Add up all those intensity, okay? So one is minimum, then two are maximum. And here also, if you consider this is minimum, and if you consider this point somewhere here, it will be, so it is having maximum intensity. This one also having maximum intensity. So like that, if you add all those intensities at different points, then we will be getting a different, very complicated kind of aspect. So that is what will happen when you are having many number of frequencies because we are not dealing with a particular frequency. In FTIR spectrometer, we are considering from 400 centimeter inverse to some 4,000 centimeter inverse, okay? And below also. So not only from even start from 200 or 0 centimeter inverse itself. So normally some hundreds or 40 centimeter inverse also. So for less than 400 also, let's consider from your that textbook figures. Let's say that is from 700 centimeter to that 4,000 centimeter. If you consider, then you have different frequencies. Okay, correspondingly, we have large number of frequencies inside. So all these frequencies are coming and hitting on that beam splitter at a single time, okay, at a fraction of time. So all these process interference and all those things will happen within 1 second. Okay, so all these process will happen within 1 second, and the computer will analyze. And if you want to that drawing and all those things, then all those things will take a few seconds. Okay, some 15 seconds. Within some 15 seconds, you can get the complete picture. You will get complete in the program from the computer. Okay? But in conventional case, if you are drawing by using that prism and the grating and all those things by using conventional IR spectrometer without FTIR spectrometer, without a Fourier transform technique, then it will take a few minutes. Yeah, then after drawing on all those things, if you're considering some 10 minutes, it will take 10 minutes to 15 minutes it will take in conventional case. But in FTIR, it will take 1 second. So that is the main difference between FTIR and conventional infrared spectroscopy, because this FTIR will give you the data, the spectra within 1 second. Not in 1 second. It will be evaluating it within 1 second, and it will be giving you spectra within 15 seconds, 20 seconds. And if you want to take n number of such scanning, okay, some 100 number if you want to take, for example, if you want to take 100 number, then it will be taking only 1,500 seconds. Okay? So many number of scanning can be performed within FT by using this FTIR spectrometer within some minutes. Okay. And it is, I think it is observed like you can take some 32 scans per minute, at least some 32 scans per minute, 1 minute. Okay. So within 1 minute, you can take 32 scans of the same sample. So which means that 32 spectras you can add up all those 32 spectras to minimize the noise, all those things. So these are the advantages. So we will go into that, these advantages of the IFTR spectrometer. So I hope you understood this concept. So we'll be having a large number of such frequencies, mu1, mu2, mu3, mu4, etc. A large number, and that is very large. We can't imagine that how complex the spectra will be. And the after this interference, okay, after this interference only the radiation will be going to the sample. Okay? But that, so if you consider this figure, okay, so I will just erase this. So where this interference will happen, this interference will be happening at this birefringence. Sorry, not birefringence. This beam splitter position. Okay, so here all those interference will happen. That all those radiations, not only this point, the radiation will be coming from here also. So we have to align that in particular point in such a way that it will come to this zero and all those things. That alignments also we have to take care of that. So this point, at this point, they will be interfering. For example, from this figure, all those radiation will be interfering at that point, and that frequencies from a wide range of spectra, that is mu1, mu2, mu3, n number of frequencies, they will be intersecting at that point and coming to from this mirror, this M1 and this is M2. So with respect to this M1 and M2, that M2's motion, okay, not that M1, this is M2 will be moving. So with respect to M2's movement, those frequencies will be interfering because they will get the path difference. Okay, and each of them will be having different path difference. They will be interfering each other. Mu1, for example, like in this case, if you are considering a single wavelength with respect to that path difference, there will be constructively or destructively interfering, resulting in maximum intensity and minimum. And so each of these frequencies will be interfering like this. Okay, and all those interference will give you a cosine kind of variation of intensity, as we discussed earlier. Okay, this kind of intensity, all those interference will give you this kind of intensities. And after those interference of different frequencies, all these interference pattern, these things, they will also have to be add up each other, and that complex spectra, signal that is going to, so that spectra will be very complicated, something like this, and that will be going to the sample. Some of the spectra, some of the frequency will be absorbed by the sample, so we'll be getting some different kind of shape now, because some of the frequencies are absorbed by the sample, and that will be detected by the detector, and then it will be going to the computer system, and then computer system will store all those points. First, it will store all those points in time domain. For example, if the mirror moved 1,000 time 1,000 per centimeter, 1,000 position per centimeter, for example, if it is moved or 2,000 per centimeter, or in that case, let's say 1,000 for PC calculation, which means at 0.001 centimeter per uh, position change, it has to take step size, it has to take first 0.001 centimeter, right? And all those, all that time, in all those time, the detector has to pass to detect what is the frequency system. So all those times it will be storing data, and we will get 1,000 number of points, 1,000 number of points, and that will be stored in this system. First, it will be stored, then it will be converted into frequency by that Fourier transform technique, and we will get that Fourier transform IR spectra of this. So that is the idea behind the Fourier transform spectroscopy. I hope you got some ideas, and you read the textbook will not cover this kind of. I don't think this moment of entry, they will just say that interference will happen like that, but this is what is happening. Yeah. Okay, anyway, so we will discuss the advantages of FTIR. I will just quickly go through this IR FTIR spectroscopy advantages. I will not discuss much. We already discussed many points of in this section. So advantages of FTIR. So first one is that only one moving part. One part. Okay. In IR and in conventional IR, we have different parts to move in this time. So we have to move adjust the angle of the prism or the grating. In that case, similarly, we have to adjust different components in that. Also, we can say there is no slit in this case. Okay. So you explain these things. I already told what is the use of this slit. Slit will make that incoming radiation to fine form, and that will be falling to the detector also. So the energy will be reduced in this case. Okay, I will just write it like this. Energy will be reduced in this case. So it is not a good spectrometer because the energy, all the infrared radiation we are not considering. But in FTIR we are considering all the infrared radiation we are not considering. Slit. In conventional IR spectrometer we are using slit and we are passing the IR radiation through the slit because slit will increase the if it is fine slit then it will increase the resolution of that conventional IR. So but we will not get full energy of the IR spectrum in conventional IR. But in this case, FTR, we are not using any slit. So energy will be, full energy will be here. We'll get all those energies corresponding to that application. Okay. And the resolution of our FTIR spectrometer is constant. It is not advantage, it is also an advantage, but just keep it. Okay. And third one. Also, we will not use any filters, filters also. We cannot filter, we don't have to filter some particular frequency. Because all frequency will be falling in the it will be all those frequencies will be appearing every and the third point is that this will be having near absolute frequency accuracy. The accuracy will be high and it is better than 100. So the accuracy, if you are considering, and fourth one is that signal to noise ratio is same. As in case of we can write same signal to ratio, or you can write just by n. In as in dispersive IR spectrometer. So whatever I am saying about that conventional IR spectrometer, which is nothing but dispersive IR spectrometer, because we are dispersing all those radiation. Spectrometer that is within is in a fraction of time. So that will be obtained very quickly in this case, and this saves time. That we already explained how it can save time. So this will be scanning within by taking all the frequencies at a single time. So, as I discussed, 32 scans per minute is possible. And then we have a single beam spectrum is ratioed against the stored background. So we will get here much more high accuracy also. There is also one double beam technique in your textbook that just you read that also. In double beam technique, what we use that in that technique is that basic concept is that some 50% of the radiation will pass through the sample, and the remaining 50% will pass in some other direction, and we will compare this at the output end. Okay, so we'll get some radiation which is missing from the instrument. So that is the basic of double beam spectra. So let's say this is your IR source. It will be like this. Let's say this is your IR source, and the IR source will be you all the spectra. And from this, from 50% of those spectra, that means intensity. So that will be going this way, and the remaining 50% will be going in some other way. Let's say this is your and this is your. Okay, so 50% will be going to the sample. This, for example, this is your sample, and this is going to directly detect. So this will be detected. So after sample we have here. So in this case, what will happen? I am just roughly drawing these things. There are some other different. So if you are considering this kind of technique, then we have original spectra here, and we have the spectra which is coming through the sample here. So now if you are analyzing these two, comparing these two, you can see some things which are missing. So that is the basic principle behind double beam spectrometry or double beam spectroscopy. So that is also there in your textbook that I didn't explain because I don't know whether. So you just check that also. It is within one page. That is not a big deal. Okay, so another advantage is that manipulation. Then sixth one is that many other operations, like summation of signal to reduce noise. Reduce noise is possible. So this is possible in IR FTIR spectrometer if you are using that, because we are having that system, and the system also allows you can write it as a 7 advantage. It also allows you to remove the background spectra or any other, like what we discussed for the case of solvents. We can remove that solvent. From that solvent, we can remove that. Sorry, if you are using solution, then we can remove that solvent spectra. If your sample is solute, that kind of addition and subtraction of spectra is possible in FTIR spectrometer. Okay. So all these things we already discussed. So many points we already discussed. So just check that. And also in your textbook, some 3 points are there. So these are the basic advantages of FTIR spectrometer. And we already discussed the working principle also. And, sometimes we can call these positions also. This is corresponding to zero path difference position. Okay. So you can take that as OPD, means optical path difference. And also there are some like ZPD, which is zero path difference at this point. Okay, so these are the basics of FTIR spectrometer. You can look into